Good day everyone. Today we will talk about tangent planes and normal lines to surfaces. So, for surfaces defined implicitly by equations of the form f of x, y, z is equals to k, where k is constant, we cannot always solve explicitly for z as a function of x and y. These are called level surfaces of the function f. The gradient vector of f plays a crucial role at any point where the change of f is not equal to 0. It is perpendicular to the level surface and thus normal to the tangent plane. This gives us systematic methods to find both tangent planes and normal lines to implicitly define surface. So, our lesson objective in this video is to find equation of tangent planes to level surfaces using gradient vectors to determine normal lines and to apply concepts to surface defined implicitly. So, let's get started to our lesson. Now we have here a formula for our tangent plane. So we have the tangent plane to S at P has normal vector of fx, y, z. So its equation is f of x, x, y, z, x minus x sub 0 plus f of y in the x sub 0, y sub 0, z sub 0 times y minus y sub 0 plus f of z is x sub 0, y sub 0, z sub 0 times z minus z sub 0 is equal to 0. Other books indicate the same way, like x sub 1, x sub 1, y sub 1, but it is still the same. So for the normal line to S at P passes through P and is perpendicular to the tangent plane. Its direction vector is like this. So the symmetric equations are x minus x sub 0 over f of x, x sub 0, y sub 0, z sub 0 is equals to y minus y sub 0 over f of y to the x sub 0, y sub 0, z sub 0, or the overall function is equals to z sub minus z sub 0 over the overall function of z. In the book of Stewart, there is a special case for the tangent plane and normal line. So the special case when the surface is given explicitly as z over f of xy, where it is only in two variables, we can rewrite it as f of xyz is equals to f of xy minus z is equals to 0. Then it becomes f of x is equals to f of x, f of y is equals to f of y, and f of z is equals to negative 1. So we will see how to apply that later. And the tangent plane equation becomes f of x sub 0 over y sub 0 times x minus x sub 1 plus f of y x sub 0 y sub 0 times y minus y sub 0 minus z minus z sub 0 is equal to 0. So it is equivalent to like that. Now let's have our first example. Example 1, we have find the equation of the tangent plane and normal line at the point negative 2, 1, and negative 3 to the ellipsoid x squared over 4 plus y squared plus c squared over 9 is equals to 3. So for our solution, the ellipsoid is the level surface with k is equals to 3, which is our constant. So we have f of xyz is equals to x squared over 4 plus y squared plus c squared over 9. So we compute the partial derivatives. So we have now f of x is equals to x over 2, and our f of y is equals to 2y, and our f of z is equals to 2z over 9. So at negative 2, 1, and negative 3, we can have now f of x for our negative 2, 1, and negative 3 we have negative 1, and for our f of y we have 2. For our f of z is equals to negative 2/3. So for our tangent plane, we can have, based on our formula earlier, we apply it, we can now have negative 1 times x plus 2 plus 2 times y minus 1 minus 2/3 times z plus 3 is equals to 0. So we multiply it by 3. So we can now have negative 3 times x plus 2 plus 6 times y minus 1 minus 2 z plus 3 is equals to 0. Negative 3x plus 6 plus 6y minus 6 minus 2z minus 6 is equals to 0. And we compute it, combine the like terms. We have now negative 3x plus 6y minus 2z is equals to 18, or we can have 3x minus 6y plus 2z is equals to negative 18. For our normal line symmetric equation, so we apply the formula earlier, we substitute it to the formula, we can have now x plus 2 over negative 1 is equals to y minus 1 over 2 is equals to z plus 3 over negative 2/3. Now for our second and last example, we have for the surface z is equals to x squared plus y squared, which is a paraboloid. Find the tangent plane and normal line at 1, 2, 5 using both methods. So it means that we will apply the special case I said earlier in this kind of problem. So solution using explicit form, which is the special case, z is equals to f of xy. So we have f of x is equals to 2x, applying 1 and 2 for both x and z, so we can now have 2. And for the f of y is equals to 2y, substituting the 2, we can have 4. So our tangent plane for the meantime, for the special case, we have z minus 5 is equals to 2 times x minus 1 plus 4 times y minus 2 and goes to z. So it is equals to 2x plus 4y minus 5. So normal line direction vector at 2, 4, and negative 1. So from f of x, f of y, and negative 1. So now we have here the solution using level surface form. So we rewrite as f of xyz is equals to x squared plus y squared minus z is equals to 0, as according to the special case we said earlier. So we can now have f of x equals to 2x is equals to 2, for f of y 2y is equals to 4, and f of z is equals to negative 1 based on our special case at the point 1, 2, and 5. So for our tangent plane now, we can have 2 times x minus 1 plus 4 times y minus 2 minus 19 times z minus 5 is equals to 0 to 2x plus 4y minus z is equals to 5. So for our normal line, we substitute it. So we have x plus 1 over 2, which is our based on our tangent plane. So it's equals to y minus 2 over 4 because we have 4 here, and z minus 5 over negative 1. That's all. Thank you.